So today we are going to discuss. I am not going to talk about this. We are going to discuss about this. Okay. So generative adversarial network. How many of you know about this? How many of you know about this? GIANs. Okay. So what it does? Basically, what it does? It's a generative model. It's a generative model. It generates the new samples. So we give a training data, and it tries to understand the structure of the data, right? And then it gives you the new samples, which actually follows the same structure of this, the same structure of the input. So basically it's a generative model, which generates the new images. So first we need to train the generative model, understand the structure of the data, and it understands the structure of the data implicitly. Then it tries to generate the new images. That's the functioning of the generative model. In terms of distributions, like probability distributions, the generator generates the samples which follows the same distribution of the input distribution. So the input distribution follows some distribution. We don't know that, but generative model tries to estimate the distribution. It understands what the distribution is, and then it tries to generate the new samples. The new samples also follows the input distribution. Right? So the output samples follows the distribution, PDF, same as the input PDF. And what is the difference between this GIAN and other generative models that we have in the literature? With this GIANs, there is a proof actually. There is a mathematical proof that the generative model generates the samples which follows the distribution, which is same as the input distribution. In other generative models, such as variational autoencoder, it also generates the samples, new samples, but there is no proof. A concrete proof says that the variational autoencoder generates the samples which follows the same distribution of the input. So this is the one model that was introduced by the good fellow in 2016 or 2015, I guess. Okay, so today we will talk about this. Mainly the GIANs understand the structure of the data. So it's a kind of what it does is it does the kind of unsupervised learning. What is unsupervised learning, right? What do you mean by unsupervised learning? So the supervised learning, right? So what is the goal of the supervised learning? Learn a function. It may be a linear function or non-linear function. Learn a function to map the feature vector to the label. Okay, this is the goal of and the goal of unsupervised. So these are the tasks that you see the supervised learning. So what do you do in unsupervised learning? So you try to find the underlying hidden structure of the data. So this is what exactly the GANs do. The GAN try to understand the structure of the data. So it tries to understand the structure of the data. It tries to estimate the probability distribution that input samples follow. So implicitly, it will estimate the density implicitly. It won't give you the explicit formulae. Right? So what are the examples for the unsupervised learning? These are the examples. These are some of the examples which which do unsupervised learning, meaning that these are the methods that get the underlying structure of the data. Another way to get another way to understand, another way to estimate the or learn the underlying structure of the data is using the GANs. So GAN tries to understand, right? GAN try to estimate the density, tries to estimate the density implicitly. It won't give you explicit formulae. So we expect explicit formulae, right? But it won't give you the explicit formulae. It would give you the implicit formulae to to generate, to understand the structure of the data, right? So you can see that these are the examples. This is one way to understand the structure of the data, right? People apply K-means clustering and EM clustering, many clustering. So this is one way to understand the structure of the data. So another way to understand the structure of the data is, what you do is that you just take the data and project this onto the lower dimension. See, you can see that you cannot understand the structure of the data, but in the lower dimension you will see that clearly you can understand the structure of the data. You can distinguish the classes here, right? The 4 classes here. But in the higher dimension, you can't understand. So in a way, right? PCA, gives you more structured data. But it's a linear transformation. What it does is it takes a sample from the input space and it linearly takes to the other space. Okay. So you see that there are 3 dimensions here. 1, 2, 3. 3 dimensions are there. Now after you project, and you will see the 2 dimensions here, right? So to represent the data, 2 dimensions are enough, or you would say the 2 coordinates are enough. So here you have 3 coordinates to represent data, and here you can you can see 2 coordinates are enough to represent the data. So this is one kind of approach. Where you can see the you can understand the structure of the data. Similarly, the same thing you can see with the autoencoder. So autoencoder also does the same function, but the difference between the autoencoder and the PCA is autoencoder does the nonlinear transformation, but the PCA does the linear transformation. Both do the same thing, both does the same thing, but it has extra block here. You can see here this is the autoencoder. It consists of encoder and decoder. So encoder takes the input data, and it gives you some representation here at the output. This is called the lower dimension space, where you can see some structure in the data. So from this data you try to reconstruct back. The formulation is different here, okay, and the formulation different over there, okay, but both do the same same thing, right? So the purpose, of course, this you can use it for generating new images, but with this you get you don't get that much good results. This is a bad generator. The reason is that the encoder only gives you the discrete space. So from the discrete space, if you sample vector and give it to the decoder, it will badly reconstruct. Okay, It's a lossy kind of, it's a right, lossy kind of thing, and yeah, it won't do. It generally, this autoencoder is not used for generating the images. So the extension of this is a variational autoencoder. So a variational autoencoder is used for generating the new images. So but especially this autoencoder is used for for extracting the features. So what you do, right, you just train the encoder and decoder. After you do the training, you just remove the decoder part and take the encoder part to extract the features, the relevant features. But whereas the variational autoencoder, what you do after the training, you throw the encoder, you use the decoder to generate the new images. So that's what the same thing we do with the GANs. But what is thrown is we'll see that. Okay. So another way of looking at the structure of the data is you just estimate the density, right? So right, what are the methods available for estimating the density? So we have parametric methods, non-parametric methods. There are many ways to estimate the density. But these density approaches that we have, right, give you explicit formulas. Okay. So this also, once you estimate the density, right, you with the with those densities, you can always test the data using those densities. I mean, right, this is a kind of estimating the structure in the data, right? So next one is yeah. So this is the the traditional methods are I already told you that the parametric methods, non-parametric methods. But there is a way to generate, there is a way to estimate the densities using the generative models. So I already told you what is the generative model. Generative model, what it does is they generate the new images. These are the new images. You see here, they are the new images. Right. These new images follows the distribution, which is the same as the the input samples distribution. So the aim here is that with the GANs, we wanted to learn a model, right, the P model of X, right, which is same as the right the P data of X. That is the aim of the generative model. So generative model generates the new samples, right, and the generated samples follow the same distribution as this. So basically we wanted to learn, right, the distribution which is same as the input distribution. So addresses the density estimation. It won't, I already told you, it won't give you explicit formulae, but it gives implicit formulae, right? Implicit in the sense you can generate implicitly. You can see the right implicit density estimation. Okay, so that same thing I have mentioned here. You can see that. So it only does the implicit density estimation, so that you can see here. This is the definition of the generative models. So there are many generative models in the literature. The popular generative models are, these are the three popular generative models, recent generative models, right? This is the one which is the very recent one, which has more advantage than the above two generative models. If you want to know the taxonomy of the generative models, you can find in the book written by Goodfellow. So what the generative model does? What we can do with this? We can do many things with the generative models. We can do the right. We can do denoising. We can increase the spatial resolution of the image. Right. So we can do. We can use these models to generate new images. to increase the data. So many more applications we can see with the generative models. So what is the GAN? Now what it consists of? What is the definition of the GAN? So this is the definition of the GAN, right? So you see that there are 3 terms in the GAN, and these are the descriptions about each term in the GAN. So the G means generative, and A means adversarial, and N means network. Okay. So basically the GAN consists of 2 networks. One is a discriminator, other one is a generative network. These 2 networks, they fight each other. They always fight each other. I'll just give you a simple example later. I can relate, I can bring the analogy with the example. So first to understand what these 2 models do in GANs. I already told you that there are 2 models in the GANs. One is a discriminator, other one is a generator. What the discriminator does? Discriminator discriminates the 2 classes. Discriminator is like a binary classifier, 2-class classifier. It discriminates the 2 classes. We already studied about the binary classifier. So the discriminator is like a binary classifier. It discriminates the 2 classes. Okay, it will say real or fake. What the generator model does? Generator model generates the the fake image or fake sample, and it gives to the discriminator. Discriminator says the sample coming from the generative model is a fake, but the discriminator says that whatever the sample coming from the generator is a fake. But the generative model wanted that fake sample to be classified as a real sample. So it says that the discriminator says that whatever the sample is coming from the generator is fake. I would say, right, strictly I would say that whatever the sample is coming from you is a fake. But this guy says, the generative, right, this says I generate a fake, but you have to take it as a real. So you have to discriminate that as a real, right? So this is something like, I will give you just analogy with the example. So let's say I am a thief. Okay, I am a thief. Sir is a police officer. Okay, right? What I do, I do mischief things. I generate fake activities, abnormal activities. But sir tries to catch up that. Okay, right? But what sir says is that I am thief, so whatever the activities generated from me is a fake. Sir always says that. Sir is a police officer, he knows that I am thief, right? He knows I am thief, so whatever the activities I generate, he says that activity is a fake. But what I wanted is, as a thief, I generate, I generate abnormal activities, I do the abnormal activities, and I want the police officer to take those activities as a normal activities. If the police officer says that I am fake, then I'll be the loser, right? When he gets lost, if he doesn't discriminate, my activities are fake, right? So I'm a police officer, I'm a thief, and sir is a police officer. So sir wanted to become a police officer, I wanted to become a thief, okay? And that way we get trained, right? So these 2 models get trained, right? We get trained, sir as a police officer, and I'm like a thief, okay? But after the training, what happens? I don't become a police officer, I don't become a thief. Sir won't become a police officer. That's what happens. This is what happens in the GANs. So after the training, After the training, this starts generating new images. So it won't become a thief. It will start generating real images. The discriminator unable to discriminate the the sample coming from me, coming from the generator. Then the training stops. So what we have to show is that, of course, we need to show, there is a proof, mathematical proof in Goodfellow, right? What it says is that the generated samples, right? So this generator generates the generated samples which follow some distribution, and that distribution is same as the input distribution. After the training, after it will set, these model settles down, right? What happens is that this generative model generates some samples which has some distribution which is same as the input distribution. So what is that we need to? That's what we need to prove. Okay, mathematically, what people have proven is that they have proven that the distribution of this is the same as that. When that happens, see, if the generator starts generating new samples, right, the real samples, right, and then the discriminator unable to discriminate. Okay, so what basically what we have to show is that ultimately this is useless, and this starts generating new samples, the real samples. That's what we need to show. When I say the generator, the GANs generates new samples which are of like new samples, which are of real samples, which follows the same distribution as the input distribution. What we need to show is that mathematically is that this generator generates the new samples, and discriminator cannot discriminate the sample coming from this and the real data.
Go back there, please. Is the discriminator acting like a teacher here?
Yeah, like teacher or
to create better and better samples.
No, it only discriminates the two samples. What it says is that the job of the discriminator is discriminate the two samples. Okay, so it says that whatever the sample comes from the generative model is fake. What it strictly says that whatever the sample, it does that. Okay, it does that. In the training process, we get loss function, something like that, and we try to minimize or maximize that loss function. Okay, right? And the job of this is it generates the fake sample, but it wanted the discriminator to take it as the real sample. So when this gets lost, see, there are two losses here: the loss for the discriminative model, the loss for the generative model. When discriminator gets lost, if it cannot, if it says, right, if it says this sample, the sample coming from this is the real, this gets lost. When this gets lost, there are two losses here. So we find the two losses and we combine the two losses, and we try to minimize the losses. So when this gets lost, if this generates a fake sample, right? If the fake sample is classified as fake sample, generator gets lost. This generates a fake sample, and if discriminator says that it's a fake, who will be the loser? Thief will be the loser, right? See, he would like to do abnormal activities, and he want this guy to take those as real activities. If that doesn't happen, then this generative model gets a loss. This has a loss and this has a loss, and this is a right. We already seen the loss for this. The discriminative model is a binary model, binary classifier. We already seen what is the loss for this, and we have not seen what is the loss for this. So maybe you can see mathematical proof. So what we do is that, okay, before we see the mathematical part of the GIAN, the mathematics would be seen in the Goodfellow book. But however, my student me, I sat together and derived, which is same as that, more of, but is slightly different from what you see in Goodfellow. Okay, so I have given the math of that. We have proved that generator, generator generates the new samples which follows the same distribution as this. Okay, after minimizing the cost function. So before we see the mathematical part of the GANs, we see what the GANs try to do, right? So as I said, so this is my distribution of the input. Okay, this is a generator. Generator generates new samples, and you can see the distribution of the generated samples, which is actually same as that. Okay, so ultimately right, after the training, so this would start generating a real like samples. And what the input to the generator, usually a sample from the normal distribution. Of course, it depends upon the application, what you wanted to do. Okay, so right. Okay, this is a block diagram of the GANs. So we have a discriminator here, and we have a generator here. And what is the input of the discriminator? 2 inputs. One input from the real samples, and one input from the generator. What is the job of the discriminator? Discriminates it 2 classes, 2 samples coming from these 2. What is the job of this one? The job of this one generates a fake samples, and it wanted this to classify it as a real sample. And if it doesn't that, it gets lost. If right. And if the discriminator says that this is a fake sample, this gets lost. So 2 losses are there. One loss for the generator, other loss for the discriminator. So this discriminator always wanted to do that. They conflict each other. Okay, so they fight each other, but nobody wins at the end. So this guy want to be like a want to be trained like a police officer, but eventually after the training he won't be a police officer and he won't be a thief. Okay, so he won't be a thief means this guy starts generating new samples. So everybody in this
finally they understand each other and then
this is what we wanted in society, right? See, if everybody is good, what is the job of this, right? What is the job of police officer? No, nothing, right? So so police officer is useless, right? So that's what right? So this is and you see that the input to the generator is the sample from the latent space, but it depends upon the applications, right? We'll see we'll see one of the applications, which is a visual segmentation using a GANs, wherein the input of the generator is the fundus image. Okay, so we'll see that. Okay, this is one of the study case. So right, the MNIST data. So it consists of different types. Okay, and we give this is the input data. This is the original real samples, original data, and we give one sample from the real sample to the discriminator. One of the input to the discriminator is from the real samples, and this is the generator. Generator generates a fake sample. Okay, initially it generates a fake sample initially, and then we give both to the discriminator. Okay, this is a real sample and a fake sample. Both we give to the discriminator. This is the discriminator, 2 samples. So at the end of the training, right, so this becomes useless because this will be exactly like this. This is unable to discriminate between this. Right, we train this as a discriminator, which has to say that the sample coming from this is a fake and the sample coming from this is a real. But what happens is that the way we take up the loss function, the way we minimize the loss function, what happens is that, so ultimately this discriminator unable to discriminate, and this generator starts generating the new model, the real samples. So after the training after the convergence, what would happen? This sample is same as this. The sample that you see here is the same as the real sample. So okay, I'll come to this. This is what happens. Well, this is a overview what happens in what happens during the training. So this is the generator, this is the discriminator, and this is the these are the samples which follow some distribution. Okay, and the output of the generator at each iteration. So at 10th iteration, the distribution of the samples more or less is not equivalent to the distribution of this, but if you see that after 10,000 iterations, somewhat this is similar to this one. The distribution is same as the distribution of this, and the input to the generator is a sample from the normal distribution, standard normal distribution. This is a latent space. So you usually you give a sample from the latent space to the generator. So this is how you can train. You already know. So what we do, we use the same algorithm, backpropagation algorithm here as well, because we use, so the two models that we see here are the networks, two networks which are CNN networks. This is CNN network, this is CNN network. It need not be CNN networks. Note that these models need not be the CNN networks. These can be any nonlinear models. But usually we use CNNs because CNNs are efficient. Okay, we have the efficient computational algorithms to train the CNN networks. Right. So usually these networks are CNN networks. So we use the backpropagation algorithm to train these. So what we do is that what we do is that a particular iteration we may fix the generator parameters and we update the discriminator parameters. In another next iteration, what we do, we fix the discriminator parameters and we update the generator parameters. So this way you can do the training of the GANs. Anyway, I have the code for one application, so you can see that. I'll forward to you. You can see that. Okay, so now the last function for the GANs is right. I don't know how many of you like math, but we are getting into the math. As I said, so discriminator is a binary classifier. Okay, discriminator is a binary classifier. Okay, so we know how to get the loss function for the discriminator, and you see that loss function for the we need to anyway, right? Okay, this is required. I don't know, this is going like this. I think here, but some part of the slide is missing. Anyway, right? So this is discriminator loss is this. I don't know how to scroll down.
Just put escape, will come out like that.
Okay, so yeah, this is better, I think, I guess. Okay. Okay, so we know we have already studied the loss for the binary two class, binary class, the binary classifier. You see that the loss function is this. It's a cross entropy. Okay. This is for the this is the loss for the class 1 and loss for the class 0. You combine these two. We already studied it. Some time back, I just mentioned about this. So you just combine this and you get the loss function for the binary classifier. So this is the loss for, you can relate this loss to the discriminator loss. So I already told you discriminator is a binary classifier. It would give you two probabilities. One probability for the real sample and one probability for the real sample and one probability for the sample coming from the generator. So these are the two probabilities. Okay. So using those two probabilities, you can define the loss functions. So here this is a loss function for the class 1. Okay, and this is a loss function for the the class class 2, class 0. This is the loss for the the sample which has coming from the generator. Okay, so you see that this is my cross entropy, and if all the samples follows a particular distribution, then you can see that the loss function can be written like this. Okay, so this is how you can anyway, right? So this is about the loss function for the discriminator. Now loss function for the generator. When the generator gets loss, generator gets loss if the discriminator says that whatever the sample coming from you is a fake. Okay. So what the generator wanted is, it generates the fake sample, and the generator wanted discriminator to give one probability. You see here, we want the generator wanted discriminator output would be 1 for the sample generated by the generator. So if this to be 1, then the term that you see here, of course I don't want to I'm too much I don't know.
Plus is there, plus so that you can enlarge this.
Enlarge.
So that after it is scroll. After that it is scroll.
Oh yeah, here, right, yeah. Okay, so you would see that so this is a loss function that you see for the discriminator. There are two terms here. One term is this, another term is this. So this term is in terms of the generator sample from the generator. Okay, so you take this term and you try to, what you have to do is that you try to minimize this. Minimization of this is nothing but getting G of G is 1. Okay, right? So minimization of this is nothing but, right? If if this is 1, what is log 0? Minus infinity. Right? So minimization of this is nothing but making G of G is 1. Making the the probability for the fake sample, right, is 1 by the discriminator. So this is how you get the loss for the generator, and you combine the two losses, right? The loss by the loss from the discriminator, loss for the generator. If you combine, then the problem becomes, right, minimax problem. You heard about the minimax problem? Yeah. So the problem becomes minimax problem. If you try to do this, if you try to solve this problem, this would have the solution. Sorry, I don't want to get into too much math, so you require some more theorems, whatever, right? So to say that, I don't want to get into that. So this is very important point here. You can see that. See, the maximum value of that function occurs, at this point, and the minimum value of that function occurs. You can see that if the two distributions, what are the two distributions? If the two distributions are equal, so the min of that loss function occurs if the two distributions are equal. If the two distributions are equal, what would happen is you go to the probability. So d of x is the probability given by the discriminator. So if the two distributions are equal, the probability the d of x, the probability d of x is equal to half. What does that mean is that, what do you mean by d of x is equal to half? If this is half, you cannot separate, you cannot distinguish the two classes. If the discriminator says, discriminator gives you half probability for real and half probability for the fake sample, what does that mean? Right? It's not discriminating the two classes. So this would happen, this d of x is equal to half only if you see that we have to have a lot of things here. So that would happen if the two distributions are equal. Okay, so you can prove that. I'll give you the PPT. You can go through that. You will easily understand. But right? You need to understand some probability concepts. Okay, so maybe you can see the Propolis to understand the probability concepts. Yeah. So this is the story of the GANs. So what would happen? This is what happens. Okay. So initially, your data distribution is this, right? And the distribution for the generator, the samples generated by the generator distribution is this. Okay. So this is the distribution of the input samples. This is the distribution of the samples generated by the generator, and this is the d of x. Okay. So after updating the parameters, the discriminative parameters and the generator parameters, maybe it may be something like this, right, after some iterations, right, after updating, right, you have to keep on update that. So finally you see that the two distributions, this may be the distribution of the input samples, and this is the distribution of the samples generated by the generator. And you see that the two distributions are equal, and when the two distributions are equal, and d of x is a constant which is equivalent to half. So this is the proof given by Goodfellow. Okay. So you can find this proof in Goodfellow. Maybe slightly complicated proof you may find, but this is more of that proof only. But slightly I think this proof is much more easier than the proof that you find in the Goodfellow. Okay, so this is the any doubts from till this point? You want me to go through the math, or you don't want to math? See, I just skipped math, but you can always I'll forward you this. You can go through this. So any doubts from the GANs before we?
Suppose we use this process for image generation. They are in the distribution sense, they are same.
Yes. Yeah.
The other perception law, what we are talking about, loss and other things.
Oh.
They may not be exactly equal, like So in the distribution sense, those two are equal.
Yeah, there will always be like, see, if you want to get same distribution, right? So if you want to generate this the sample, which is the same as the input sample, so you need to give more training to that, more training data to the generative models. Otherwise, what happens? This what? This may not the error that you have here may not. See, you try to minimize this error on the computer, right?
Appearance wise, suppose I have a original image. Then I have a reconstructed or generated from this part. There could be a slight.
They're slightly different, like, yeah. There always be like. See, if you want to get more exact image, you need to increase the training data. That's the only thing you need to do. And more training data, and you need to run the algorithm till it converges. Okay. So. And in between you should not stop. Okay, so you need to run the algorithm. You need to apply the optimization algorithm till the error error is a minimum error. Okay. Again, there's a lot of problems, right? So we already told you the discriminator is a CNN. Discriminator network is a CNN network. Discriminator uses a CNN network, and also the generator uses a CNN network. Right, the problem with the CNN training of the CNN network, right? We use only the steepest descent algorithm, and right, the steepest descent algorithm tries to give a local minima. It won't give you the global minimum. Okay. So that problem also would be there. Okay. It won't really generate the new images. There will be a slight difference always. You don't get the exact images generated by the generator. So there are practical issues with this.
The discriminator, there is a decision maker, right?
Decision maker, yeah.
The decision maker is CNN or any variety of.
Yeah, any nonlinear model that you can take any classifier which does that, which does the discrimination. Generator does the regression actually. See, generator does the regression and the discriminator does the classification. So this is about the. You already know the application. See, one of the application is this GIAN can be used to segment the images. So here I have taken the problem of retinal vessel segmentation. I don't know about the fundus image, frankly speaking. Sir knows more. Sir knows better than me. If you want, see that. Okay. So the goal here is to get the vessel part, right? But these are the vessels. Okay. So what we do is that we know, right? The retinal image consists of contains the vast information about the possible diseases. So it's a need of our to segment this. So we give this input. This as the input to the generator, the GANs generator, and we expect the generator to do like this. Okay. This is the segmented part of this. So this is what we wanted to do. If you want to know about the details and all, right, you can ask sir about So I don't know about the fundus image, but I'll show you how we can do the segmentation using the GANs. See, it's simple. It's not difficult to understand. So this is the architecture that you see, which is being used for the segmenting the images. So we have the generator here. This is the generator, and there are 3 discriminators here, right? Each one handles different resolutions here. There are 3 discriminators here. 3 discriminators handles 3 different resolutions of the images. So we have the ground truth, right? The ground truth from the radiologist or somewhere, right? The ground truth is this, and what we expect generator to give the segmented output, which is same as the ground truth. Okay, this is the ground truth and this is the segmented one. So what is the input to this? The input to this is a fundus image, and the generator is a unit network. Okay, already know, right? We have already studied. You have studied about the unit. The unit architecture. So generator is basically a unit architecture, and this discriminators are basically 2-class classifier. Right? You can achieve with the CNNs, and in addition to these things, you will have some more model here, which is a perpetual loss model. So the input to this perpetual model is the ground truth and the image generated by the generator. So we compute some loss here. This loss also will be minimized. So we have 2 losses here. The loss incurred by this one discriminator, and loss for the generator. Initially you don't get the perfect segmentation, but after the training, if you give more data to this, so you may see, right, the accurate segmentation. You may see that the generated image exactly look like the ground truth. So this is right. Why we want to do like segmentation? Yeah, that right. You can see, sir can answer why we have to do the segmentation. Right? So what we wanted is, so we wanted this kind of image, okay, which must be similar to this. The GAN is capable of generating, right, the images which exactly same as the ground truth images. This is my ground truth images. So I give the fundus image, and it will give the segmentation of that. So from the segmented image, you can infer, you can take many things out from that. Okay. So you can diagnose the patient based on that. Okay. Or you can do the further processing to get more information about the diseases. So this is one of the application that you find. So this is about the unit architecture. So right, what the unit architecture. This is actually the generator. So this generator is basically the unit architecture. Okay, the unit architecture, right? So it has an encoder and decoder. So here, what the encoder does is that it tries to give you a features image which is a more structured, and from this you try to reconstruct back which is same as the ground truth. So you get some losses here based on the ground truth, and you try to you try to update, you try to modify this based on the ground truth. So this is what so this is perceptual loss, and this is the code. Okay, this code implemented by my student. This is one of the assignment for my coursework. So once one of my student implemented this. So this is the code. If you want to code, you can approach me. I'll give you the code. So this is the, this is the details of the discriminator model. So you can see many convolutional layers and batch normalization layers, and many things are there. So at the end we use the dense layer to classify the two classes. So there are this particular architecture uses different discriminators because we need to it is why this is this architecture from one paper. They used three different discriminators to handle the multi resolutions. So we don't know why they have taken that. So we have just the students just has he has implemented the paper, and he has used the three discriminators over that to handle different resolutions. So this is the code. You can see this. So that this about the GIANs and its application in medical imaging. So any doubts on this, you can just but mathematical part, if you want me to explain, I will explain, but outside, okay, not here. It consumes a lot of time to explain. So if you have any doubts on the functioning of the GIANs or the idea behind this, you just write.
What are the performance metrics used to evaluate the GIAN network?
Performance?
Performance metrics.
Yeah, I mean it has to, like, the generated image should be matched to the real like samples, right? So if it doesn't, then there will be error. I mean we get the loss right there, right? So we try to minimize that. So metrics you are saying, right? So you have to compare with the always the real samples. No, yeah, you can use what you're saying. I didn't get you exact question from you. Maybe you can use a similarity index, right, for evaluating. Maybe you can, yeah.
In the case of the retinal images you showed for the drive and stare images, the ground truth is given, so you can compare with the ground truth of the vessels marked by ophthalmologists.
Yes, correct. Yes, yeah, you can do that. Yeah. Yes, correct. So you see that exactly, right? We see that we use. See, this is to compare. See, we use a Jensen inequality. So this would give you right. Yeah, of course, this is to compare the two distributions. So overall, you would see that we need to minimize this, right? The minimum value, this is a constant, okay? And the minimum occurs, right? What is the minimum value of this? The minimum value of this is 0. This happens if the two distributions are equal. This is called the, this is similar to the Shannon divergence. KL divergence. This is again from the information theory. So you need to know a little bit about the information theory to understand this. Okay. So and we can, of course. There are a lot of mathematics behind this. So we have used some identities here. You can see here. So you know this theorem, right, from the probability theory. So this is the theorem that we have used to prove the, the two distributions are equal. So we know, right, if the PDF of random variable is G is given as this, then the PDF of another random variable, which is a function of that random variable, right? So the PDF of the this random variable is equivalent to this. This you can find in the Papulis book. Okay. So this identity, this theorem we have used to manipulate the objective function, and we have rewritten the objective function so that we can proceed further. Okay, so we have modified this one, and then but a lot of understanding is there. So you have to I don't know, you need to have the background of probability. Okay, unless you have that, you don't understand what is happening there. Okay? But the functioning definitely understand. Okay, see, if you want to know the proof, right, why the two distributions are equal, then you need to understand the loss functions and the minimization of the loss functions. So this is what Okay.
I will share two small stories, but I'll do that after you close the recording.